so today we're going to do section 8.2, the dot product of a vector. And so vectors can be multiplied in two different ways, both of which are derived from their usefulness for solving problems. We are only going to be using the dot product or scalar product. The answer to a dot product is a number, it's a scalar. Okay. The other one we'll do, you might do in some later date, in some future class, but we will not do the other product in here. So what is the dot product? If I have two vectors, u and v, their dot product written this way, with a little dot symbol between them, is literally take the first components, multiply them together, multiply the second components together, and then add those two results together. And so what you're going to end up with is a number. So the dot product of two vectors is a number. So fairly simple. Here are some properties that are useful. I have three vectors here. K is a scalar. And what this is telling me, this is basically the commutative property of dot products. That means the dot product in one way is the same as the dot product in the other. If I dot product a vector to itself, it's just the magnitude squared. This is the zero vector to any other vector. A dot product produces the number 0. This right here shows you the associativeness of dot product. And this right here shows you the scalar multiplication of a dot product. So if I do a scalar to any one of these, it's the same thing as doing the scalar to the dot product. Multiplying. Orthogonal vectors. Orthogonal vectors are where the dot product of them is 0. So if I have a dot product that is 0, then they are called orthogonal. But what does orthogonal mean? Well, basically, it's very similar to perpendicular. In almost all cases, except for really one, orthogonal means perpendicular to. So that means these two vectors would be perpendicular to each other if their dot product is 0, provided neither one is the 0 vector. So the reason why perpendicular and orthogonal are not exactly the same thing is because of the 0 vector. A 0 vector has no direction, so it can't be perpendicular to any other vector. Okay, it can't be perpendicular. But the 0 vector is orthogonal to every vector. Okay, the dot product with 0 vector is always 0. So therefore, it is orthogonal to all other vectors, but it is not perpendicular. So that's the one example where they differ. So we can't say that orthogonal always means perpendicular, but for the most part, it does. So let's look at some examples. So let's find the dot product of these right here. So here's two vectors. We're going to do the dot product between those two vectors. So literally, very simply put, you take the two front components, -2 times 4, and we're going to add that to 3 times 5. And I recommend that you write it this way so that you get your signs correct. -8 plus 15 and 7. So there's your dot product. So those are in component form. These are in linear combination form. Same process. Take the front. So it'd be a 2 times a -3. And to that, we're going to add a -1 times a 2. Remember, coefficient here is -1. So this is a -6 plus a -2 or -8. Okay. This right here is, are they orthogonal? Remember, if they're orthogonal, then these two, the dot product of these two vectors should be 0. So let's find the dot product of u and v. So I have a 5 times a -12 and a -6 times a -10. And so the first one is a -60, the second one is +60, and sure enough, they are orthogonal. So there you go. Okay? Another tool that we can use with dot product is the angle between two vectors. If I have two vectors, theta is the angle between the two non-zero vectors, u and v, then I can use this to help me find that angle, this relationship. So I'm going to use this formula right here, and we're going to find an example of it. So here I gave you two vectors, u and v. I graphed them so you can see what they look like. Okay? And so the angle that we're talking about, that we're trying to find, is this angle between them. Okay? And so this one right here is -6, -3. This right here is -8, 4. And so to find this right here, we need to find and use this formula. So u dot v, u and v. So these are the magnitudes, and that's the dot product. So to find this, we have to find these values right here. So what is u dot v? Well, it's going to be a -6 times a -8, a -3 times a 4. And then we work this out. This right here would be 48 minus 12, 36. Okay? So then we need to find the magnitude of each of these vectors. So what is the magnitude of u? That's the Pythagorean theorem. That squared plus that squared, so a -6 squared plus a -3 squared. And we want to work that out. So that's 36. That is 9. Looks like 45. Simplify. 9 times 5, so this would be 3, the square root of 5. The magnitude of v, -8 squared plus 4 squared, 64, and 16, 80. And then we simplify that. This is 16 times 5, so it'll be a 4, the square root of 5. So we bring all this information into our formula right here, and we'll get the cosine of our angle is 36. And then down here we'll have a 3 square root of 5 and a 4 square root of 5. And so if I work the bottom out and multiply things, so it's going to be a 12 times a 5. That'll be 60. And this reduces down to 3/5. And so the cosine of our angle is 3/5. So we can do our cosine inverse of 3/5, and we can get an approximate value for our angle, which will be 53.130 degrees. And there you go. Okay, so about 53 degrees. And if you look at the protractor here, I try to draw it nicely so we can see this. I'm slightly off. But if you look closely over here, you can see that we're kind of pointing out to that area of 53. Okay? So that's how that formula works. So what's next? So in the previous lesson, we used vectors can be expressed as the sum of a horizontal and a vertical vector. Okay? So here's vector v. I can look at this vector, the horizontal one, and this vector is the vertical one. So the sum of these two vectors, this would be the resultant of it. And so v is the sum of those two vectors. Okay, the horizontal direction and the vertical direction. This is useful when we're trying to solve problems that require us to find how much of the force along a certain vector is going in a horizontal direction. Okay, here's an example. This is a lawnmower. If I push the lawnmower down on the handle like this, so I'm acting a force in this direction, but part of that force can be broken up into being pushed downward and also pushing forward. This is what propels your lawnmower forward. Your effort here, but not all of your force is being pushed along that way. The only time you're going to get it exactly is if I push exactly in the direction I want it to travel. Then the whole force is going in one direction. But as we know, for a lawnmower, that's very inconvenient to be laying on the ground pushing it. So we push on the handle, and we get this force that pushes it along. So that's what's useful about being able to break it up into a horizontal and vertical components. This is a simple concept of this part right here, which is called the projection of a vector u onto a vector v. So we're pushing this, and we want to know how much of this force is being used to push it forward. That's what this is referring to. The difference between this one and this one is that this one is in a horizontal form. Horizontal is the vector we're going to project onto, and this one is for any vector. So that's why it looks a little bit more complex. So here's an example illustration. Let me walk you through it. Here's a vector projection of u. Here's vector u onto vector ps, or vector v here. The directed line segment ps, p. So what we do is, here's this force, and it's basically kind of like a shadow effect. If I push along here, how much of this force is along that line? If I wanted to push something up a hill or something like that, okay? And so you take the endpoint, you drop a perpendicular to the other vector v, like so, and that point r is created. That is how much of this vector is in that direction. The other part of the force in that direction is this part right here. So u can be broken up as a vector pr plus rq. pr and rq are perpendicular to each other. And this is the amount of force, or the projection of u onto v. And that's how I can find that value. So you can see that this is a portion, the length of this is a portion of this length. And so that gives me that relationship, that proportion there, or that ratio, I should say. So the projection of u onto v can be found for this, and that's that little piece of that. And so in the lawnmower example, PR would represent the horizontal direction. In general, PR is in the direction of PS. So this is in the direction of that vector is what it boils down to. So I'm going to show you how to walk through this formula. So I'm going to do another example for you and show you how it goes through the process. So first thing I did is I drew both vectors. Here's vector u and vector v. And I want to know the projection of u onto v. How much of this vector right here can be projected into that direction? Okay, so what you do is you drop the perpendicular. So from this point, negative 3, 5, draw the perpendicular from that point to the vector v. And that produces the endpoint of the vector you're looking for. So I'm looking for that one. That is the projection of u onto v, a very small piece. All right, so w is the projection of vector u onto vector v, and I can find that using the formula that we were given. The dot product, the squaring of the magnitude on the bottom, and then times it to vector v. Because w is on v, but it's a shorter, in this case, it's a shorter piece. So this right here will shorten the magnitude of v. Same direction, different length. So we got to find all these pieces. We got to find the dot product of u and v. So it is going to be 3 times 6 plus a negative 5 times 2. So this is 18 minus 10, 8. We need to find the magnitude of v. So that will be the square root of 6 squared plus 2 squared 36 plus 4, 40. Now we're going to square that, so that will just become the 40, because the square root of 40 squared is 40. And we plug these numbers in, and so we get our W is going to be 8 over 40. And we're going to times that to vector V. And so this right here is 1/5. And vector V is 6, 2. And so our W then is this vector, 6 over 5 and 2 over 5. And there you go. So W is a constant force. And W is the amount of this that is in that direction. The last part of our lesson in this one is work. The work W done by a constant force F acting along the line of motion of an object. So the work is the magnitude of the force times the distance that it travels. Since this force is acting in the direction of travel, the whole parts of the force is in that direction. So it's just the magnitude of this force times the distance traveled. That's the distance traveled. If the force is applied at an angle to the line of motion, then we have to change the way it looks. I guess I didn't put another picture here. But the other one would be the same picture. Here's P and Q. And here's the line of travel. And then now the force is acting in this direction at an angle to the line of travel. Okay? And so then we have to find that component part that's down here, that projection of this force onto this direction. Okay? And so from that, there's the magnitude of the projection force. So that is what is the magnitude of that force times the distance traveled. Well, this is the right triangle, so it's going to be that formula right there. Or you can just do the dot product if you know the two forces. Most of the time we will do this one right here. Okay, because we'll know the angle in which it's traveling, which is what the next examples are going to show you. So in this particular case right here, there's a barn door. Okay, we're going to pull it across and close the door. Here's the opening over here. And we're going to slide that door over to that position. We're going to pull on this rope right here at an angle of 60 degrees. We're going to pull at a constant force. And that force is going to be a force of 50 pounds. So what that tells me is that the magnitude of F, the force along this line, is 50. And our angle is 60 degrees. So if I want to find the work, I'm going to travel at 12 feet, then I'm going to use the formula for our work is the cosine of our angle times the magnitude of our force times the distance that we are traveling. And we just plug our numbers into this. So the cosine of 60 degrees times the 50 times the 12. Cosine of 60 is 1/2. And so we multiply this out and we get an answer of 300. The force is in pounds, the distance is in feet. And so you get this work unit process, and it is called foot pounds. Foot pounds. You're going that many feet with that force of 50 pounds. Okay, so that's how you write the units for a work problem. We have another example down here real quickly. We're going to move an object that's sitting right here. We're going to move it all the way over here, so that's sitting right here. Okay, we're going to move it 5 feet. We're going to have a force along this line right here. We have a force going in this direction that is going to have a magnitude of 24 pounds. Okay, and so what part of this is in that direction? That's what we need to find. And so we need to find that angle because we don't know it. So that means I have to find the direct angle of this vector because our force is in the same direction as that vector. So what is that going to be? Well, what is the tangent of this angle? It is 5 over 4, E over A. And so our angle is the inverse tangent of 5/4. Okay? And so we use our calculator. We find theta is approximately 51.34 degrees. Now that I have that, then I can use my formula for the work, which is the cosine of the angle times the magnitude of the force times the distance that we are going to travel. And we just plug our numbers in. What is the cosine of 51.34? A force of 24 pounds and a distance of 5. Okay, you multiply all that out and we get an answer for our work to be 74.964 in foot pounds. And that's how that's done. Okay, we'll be doing more problems together in class. There's the end of this lesson.